Okay, good morning and welcome to my presentation on the topic of a multi-physics-informed learning algorithm. Okay, is this a good start here? Good morning and welcome to my presentation on the topic of a multi-physics-informed learning algorithm for vadose zone transport modeling. This work was funded by the Laboratory Directed Research and Development Program at Pacific Northwest National Laboratory. So the outline of my talk comprises a background which includes a brief review of past and current studies, aim and objective, describing how this work differs from others, the algorithm which introduces three key components, and then some results comparing known to estimated parameters using the algorithm and comparing traditional to reduced order model simulations. So numerical vadose zone transport models require an inverse process to estimate parameters that cannot be explicitly represented. Combining the state measurements such as pressure head, temperature, and concentration in a multi-physics inversion is known to improve the property estimates given the presence of mutual information content. Some of the ongoing numerical modeling challenges that we come across include identifying influential parameters, identifying calibration data with mutual information, high performance computational resources necessary for multi-physics subsurface simulations. So machine learning solves three problem classes that include data-driven discoveries, data-driven solutions, and then combinations thereof. The data-driven solutions involve using unsupervised or supervised machine learning to classify, estimate, predict, forecast, or one or more response variables. For example, unsupervised learning was used to estimate continuous subsurface hydrogeophysical properties, whereas supervised learning was used to predict subsurface nitrate contamination, groundwater recharge, and groundwater redox status. There has been also some work done more recently using deep neural networks to predict groundwater recharge and forecast groundwater levels. And in the wake of these and other data-driven studies, there's a growing consensus that machine learning needs to respect the laws of physics. So physics-informed learning is an approach to combine the joint solution of numerical models whose, in this case, governing equations describe the physics of subsurface transport with machine and/or deep learning kernels. For example, my colleagues at PNNL recently implemented a multi-physics-informed deep neural network to jointly estimate the hydraulic conductivity, hydraulic head, and concentration values under steady state homogeneous conditions. The primary finding is that the physics-informed deep neural network is more accurate than the traditional deep learning neural network. Some challenges in implementing a deep neural network include things like they require a large number of hidden layers and a large number of training data. They're subject to something called the vanishing gradient problem, and they have trouble oftentimes generalizing to independent data. So in this study, the aim is to develop a multi-physics-informed learning algorithm for improved variably saturated zone parameter estimation and rapid reduced order transient modeling. The objective is to quantify and compare known estimated water, heat, and solute transport properties and simulated transient pressure head, temperature, and concentration in a heterogeneous or layered variably saturated subsurface situation or zone. The multi-physics-informed learning algorithm proposed here comprises three primary components. In the upper left is a multi-physics numerical model. There's also surrogate machine learning models as a second component, And the third component is a multi-component objective function, of which I'll briefly describe these components next. The multiphysics numerical model used in the algorithm comprises a set of explicitly coupled partial differential equations that describe variably saturated water, heat, and solute transport. The joint inversion of these multiphysics model shows that mutual information in pressure head temperature and concentration measurements improves property estimates. The figure at the bottom of this slide shows contributions of pressure head in blue, temperature in red, and concentration in yellow to property estimates, such as the hydraulic conductivity on the left and the heat capacity on the right. The surrogate machine learning models introduce a long-term field data to constrain the multiphysics-informed learning algorithm here. To test the algorithm, we conceptualized a managed aquifer recharge setting shown on the upper right. The correlated random variables are used to simulate stochastic boundary conditions that are applied to the numerical model, and resulting in stochastic subsurface pressure head, temperature, and concentration values shown at the middle panel. The bottom panel shows the complete data set, including time, distance, 12 properties, and 3 coupled state variables. Influential model parameters or features are identified based on mutual information content using learn heuristics algorithm. In this case, a series of neural networks with back propagation are evaluated using a genetic algorithm and a fitness function constrained by the 3 state variables, pressure, head temperature, and concentration. To identify the robust features, we use random restarts of the algorithm and then evaluate the parameter modes. Important model features highlighted here in yellow with mutual information are the time, distance, hydraulic conductivity, thermal conductivity, bulk density, and dispersivity. In building the surrogate machine learning models, we use a random subset of the original set of models for training with subsequent random splits to independently test the trained models. This slide shows the results for an independent testing of a single coupled 3-response model with 6 predictors. Those are those property values. This unsupervised learning model results in simultaneous unbiased estimates of pressure head, temperature, and concentration that are sensitive to time, distance, and properties. In contrast to the unsupervised machine learning algorithm I just showed, none of the supervised machine learning algorithms, including the random forest, gradient boosting regression, ensemble, gradient boosting, and Gaussian processes revealed sensitivity to subsurface properties. Given this finding, we train and test the supervised learning models to predict a single response as a function of time, distance, and the other 2 dependent variable responses. This figure shows training and testing of the supervised random forest machine learning model. The 4 panels in each quadrant indicate testing on the full training set and various random splits, including 20%, 1%, and 0.2%. The upper right quadrant reveals unbiased independent predictions of pressure head as a function of time, distance, temperature, and concentration. And similar unbiased results are shown across the splits when predicting temperature as a function of time, distance, pressure, and concentration shown at the lower left, and when predicting concentration as a function of time, distance, pressure head, and temperature shown on the lower right. The multi-component objective function is the third part of the physics-informed learning algorithm. This illustration shows the minimization of differences between the measured and predicted pressure head, temperature, and solute concentrations when using the multiphysics numerical model as the first component and the machine learning as a second component. notice here in in the second component that the random forest is used to predict the pressure head, whereas the ensemble gradient boosting is used to predict the temperature and concentration. Lastly, this multi-component objective function includes a smoothing constraint, a traditional Tikhonov regularization. Here we compare the parameter estimation layer results among the multi-physics joint inversion equations shown in green, in blue, in green, and the multi-physics informed learning in blue. There's 3 layers here, and the upper gravel layer is shown in the left panel. The middle silty layer is shown on the right panel, and the lower sand layer is in the bottom panel. In general, these results reveal that the multi-physics informed learning algorithm had 1 order of magnitude less error than the multi-physics numerical inversion by itself. This figure reveals good correspondence between the results of the numerical multi-physics simulations of pressure head temperature and concentration shown in the upper panel with the reduced order machine learning simulations in the lower panel. The reduced order model reflects training of the unsupervised machine learning algorithm using the physics-informed learning parameter estimates and stochastic boundary conditions. This reduced order model provides computationally inexpensive method to rapidly evaluate changes in boundary conditions on subsurface pressure head temperature and concentration. In summary, the proposed multi-physics informed learning algorithm reduced error in the estimated water heat and solute transport parameters by about 1 order of magnitude. And 2, it produced computationally inexpensive reduced order machine learning models for rapid pressure, temperature, and concentration simulations to inform management and policy decisions. So this brings me to the end, and if there are any questions, I'm happy to take those now.
Okay, thank you, Michael. I don't see any questions at this point, but they may still come up. So I'm just waiting for the questions to be sent to me that we're going to use during the general question period. That might take me a minute or 2.
Well, since we have a minute,
Yeah, go ahead, Mike.
Yeah, I just wanted to point out that one large advantage in using this approach is that there's actually this physics-informed learning algorithm reduced the computational burden associated with the traditional Jacobian matrix calculations by about 95%. So this reduced the number of iterations to convergence from 28 to 3. And using the reduced order model, what I envisioned in a larger scheme is the multimodal transfer learning and the application of this with geophysics to actually address that 3-dimensional estimate of continuous property values. And that some other people have mentioned about the scale dependence and issues. That's where this is going.